All right, so triple integrals, cylindrical coordinates. If we have just a basic triple integral, and it turns out what we're integrating over is a cylinder or a cone or paraboloid, three-dimensional parabola. Those three especially. If E is one of those three, cylindrical coordinates are pretty nice to use, okay? In most cases. Okay? So, I mean, involve these because, yeah, the example I have will be that. All right, so what does that mean? Well, so we're starting in, this is rectangular coordinates, right? So I've got to convert to cylindrical. Well, converting to cylindrical is much like converting from, in double integral, from rectangular to polar, right? So first of all, I would want to change fxyz to f. So x is r cosine theta, y is r sine theta, and z is z. So that's going to get that part taken care of. Now dv, like we said, dv is dz, dx, dy, or dy, dx, etc., etc. Well, when we go to cylindrical, guess what I need the d's of? d, r, d theta, dz. Well, if you remember back at polar, it's not just going from dy dx to dr d theta. It was r dr d theta. Same thing here. You'll need r dz dr d theta is usually the order there. So again, you got to put in that extra r. So again, the order that typically you want are dz, dr, and d theta. So the z's are first. So the z's, typically you have z in terms of x's and y's. Well, in this particular case, the z's are going to range from, they call it u1, x is r cosine theta, y is r sine theta, to u2. So you just have to write your z's in terms of r cosine theta and r sine thetas. All right, so r, well, since we're doing it second, it may be a function of theta. So they call that h1 theta, h2 theta, and then finally your thetas, which typically you range those from theta to beta. Anyway. Yeah, so going along these lines, we haven't, I don't think we've done a whole lot with cylinders. So let me just do a little bit, talk a little bit about what these cylinders, what the cylinder anyway. Paraboloid is just a two-dimensional parabola, three-dimensional parabola. Paraboloid is the three-dimensional parabola. We've done a little more with that. It's kind of a, if you cross-section it, it's a parabola, but so it's kind of looks like that. We talked a little bit about that, but the cylinders, here's some examples of cylinders. So that's paraboloid. know what the cylinder looks like, but as far as graph equation, what does it look like? Well, it turns out if you do, for 3 dimensions, x squared plus y squared equals, you got a 25 is one number I picked here. 3-dimensionally speaking, that is a cylinder. Because, in 3 dimensions you need x, y, z, this doesn't have a z with it. So, obviously, what have I got in 2-dimensional? It's talking about a circle, radius 5, right? So in the xy plane, it's circle, radius 5. So 5 here, backwards, forwards, whatever, okay? So I've got a circle in your xy plane. Well, what z adds to that, so that would be z equals 0, right? At z equals 1, I'd also have a circle radius 5, but at height of 1, let's put 1 here. So I've got this circle here, right? And then at radius, at height, at z equals 2, I've got a circle radius 5 at z equals 2. And then down 2. So yeah, you just get this, maybe we did do this. Now that I'm drawing this, I think maybe we did do this. But so you get this infinite cylinder, cylindrical shape. So that's one example. I overlap my equation there. All right, now if we, what if we had, again, 3 dimensions, x squared plus z squared equals 16. Well, in that case, we've got a circle in which direction? Or which plane? The xz plane, right? So you got circles in the xz plane. Then the y's vary. So anyway, here's what that turns out. So it's not a cylinder like this, is it? In the xz plane, I've got a circle radius 4. So x is 4, z is 4, negative 4, so forth. So I've got this circle in the xz plane, which is kind of at an angle there. But the y can vary, and so, you've got these radius 4 circles, but y's are varying. So yeah, it's a 2 cylinder like this. Part of my drawing here, but yeah, so you get this 2 more like this. These are kind of hidden, but it's easy to draw. Got that established. So the tube's more like this, so it's an infinite tube sideways. And then of course you can have the tube on the x-axis if you have the x and z. So anyway, our cylinders probably would be more like that, but I just wanted to mention that.